Hello, this video is on OpenRail Operational Analytics Linear Decision Support. We'll talk about track curvature, superelevation, Cant deficiency, and speed through a curve, and the fact that traveling too slow will actually increase your maintenance costs. When we talk about superelevation, superelevation is a difference in height between the left and the right rails. It is generally applied in curves, with the low rail being on the inside edge of the curve. It is applied to offset the lateral forces that are felt when a vehicle traverses a curve. When we look at Cant deficiency, the amount of Cant deficiency is expressed in terms of required superelevation to be added in order to bring the resultant force into balance between the two rails. Cant efficiency can be introduced for several reasons. One example could be that trains will traverse the curve periodically at significantly below design speed. Track can be designed so that at a certain speed, when a train travels through a curve, the passengers are pushed down on their seats so they don't feel the curve at all. The amount of force the passengers are pushed laterally is exactly offset by the amount of force the passengers are pushed into their seat because of the superelevation. For a constant speed of a running train, the amount of required superelevation or cross level to achieve this balance is called equilibrium cant. For a given speed, if the actual superelevation is not the same as the equilibrium cant, the amount of superelevation difference is called Cant deficiency. On straight track, due to the cone profile of the rails and the 1 in 20 inclination of the rail, the wheel flanges should not touch the gauge face. On curved track, this is theoretically possible with the application of sufficient cant. This cant is calculated as equilibrium cant, which is calculated using line speed and curve radius. This is undesirable in reality because the reality is the same curve is used for different vehicles of different sizes which travel different speeds. However, if most of the traffic is slow, it would be appropriate to reduce the cant to ensure that the inner or lower rail does not degrade at a higher rate. That being said, if most of the traffic is high speed, it would be appropriate to increase the cant to ensure the outer or high rail does not degrade at a higher rate. Now that we understand superelevation and cant deficiency, let's see how a transit owner and operator discovered the root cause of a constant problem with the rail degradation through their curves. This is a view into Operational Analytics Linear Decision Support. And this example shows how recording speed can also be very valuable when aligning the speed data against track geometry data. In this view, we have a track layout at the top, we have posted speed values, we have curvature information, each gray box represents a curve, and we have a speed view into the data. And let me explain this in greater detail. The parabolas that you are seeing are a calculation of the max speed based on the radius of the curve, the superelevation, and taking into consideration the max allowable Cant deficiency. This allows you to know exactly how fast you can travel through a curve. Below these parabolas is the equilibrium speed calculation. The equilibrium speed calculation is calculated to determine the minimum speed required through a curve. If you operate below the equilibrium speed, then you cause extra wear on the inside rail. In addition, we have red markers, which is showing the posted speed, green markers, which is showing the original design speed, and we can even add a posted is greater than design speed to highlight some of the issues. The yellow markers are showing actual speeds of locomotives. The client realized that excessive rail damage to the inside rail through some curves was actually because the train operators were traveling at lower than posted speed. So we can look into this data, and to remove the constant maintenance of the inside rail, we have a few options. We can tell the operators to travel faster through the curves, or we can redesign the curves. But without loading in all this data, we could never understand the root cause of the problem.